In this question, we are asked to draw three non-isomorphic trees on 5 vertices. Now, the thing about this is, how many vertices are there? There are 5 vertices. Now, just be clear about something, it's a tree. Now, necessarily, there must be n minus 1 edges, so there must be 4 edges. Now, just recalling from graph theory that the sum of the degree sequence must equal to 8. Just move the page here, we keep going anyway. So the sum of the degree sequence must equal to 8. Now, so let's consider this, that we have 3 non-isomorphic graphs. Now, it's very tricky to draw. No, it's actually very not tricky to draw isomorphic graphs, trees, when you have this level of information. So what we're going to do is actually draw out the placeholders for the degree sequence. Okay. Now, necessarily, the largest possible value of an edge must be 4. Okay. So let's actually try out that one. So in the first case we have 4, but necessarily the sum of the rest of the values has to equal 8. So we can only have 1s in here. Okay, because all the values have to add up to 8, and there are 5 vertices. Okay, so necessarily there are 4, and once we put in the 4, there are 4 empty vertices. The sum of that should be 4, so necessarily they are all equal to 4. Let's draw that one there very quickly. Something like that. Okay, let's do that for another one here. So now, if we draw another tree with a vertex of degree 4, it's going to be isomorphic to what we've just done previously. So let's do one with the highest degree is 3. The lowest degree is, let's say, 1. And how many numbers do we have in here? Well, let's just try out another one. Okay, we have 5 altogether. The two values must add up to 8, so we put in a 2 here and a 1 here. Okay, so we have 5 vertices, and the sum of the degree sequence is 8. So this would work something like this: 1, 2, 3, 4, 5. Actually, I'll put in the vertices in red just to make it easier to follow. Can we put in something with 3 and 3? Let's try out something like that. This is a little bit of an experiment. 3, 3. Well, the sum of the remaining degree sequence must equal to 2, but there's 3 vertices left. 1 and 1, still an empty vertex. Doesn't work. That's why you're very mindful of the degree sequence and the sum of the degree sequence. So that's not going to work. So let's try out. So that's another possible combination when you have one at the degree sequence starts with a tree, another tree, but it's not viable as a isomorphic graph tree. So let's start this one with a 2, another 2. There's got to be some 1s in it. So what would be left? Another 2. This is actually a path graph. Something like this. Okay, path graph. And yeah, path graph on 5 vertices. Actually, if you think of it, that's the one I should probably start it with because it was the easiest. Draw on a separate diagram all the non-isomorphic trees of 6 vertices by adding a vertex to a copy of each you've just drawn. I'll just do this very quickly with the first one just to get the idea across. But if you add a vertex and an edge, you can do, there's two ways you can add a vertex here. So you can add a vertex here like this. Okay. Now if, let's just say for argument's sake, I picked a different vertex to add that vertex to, or connect it to, it would have been isomorphic to the one I have already. So that's no good. The second option we could have gone here for is actually add it to this, the center vertex there. So those are, for that, the first option there, those are the only two ways you can add a vertex, a sixth vertex, by adding a vertex to the tree already. That is non-isomorphic to each other. If, just to be clear about something, the green one we have there already, let's suppose that I added one like this, that would be isomorphic to that one. So that is why we can't use it. Alright, that's that one there. So move on from that now.